Thanks everyone for joining today. My name is Michael Blonsky. I'm a research engineer at NREL. I work in grid planning and analysis with a focus on kind of demand side research and demand flexibility and load forecasting. And I'll be presenting today on the OCHRE model along with my colleague Jeff Maguire. You want to introduce yourself, Jeff?
Yep. So I'm Jeff Maguire. I've been working with Michael Blonsky on his tool for years now. I sit in the residential buildings group, and I've been there for about 15 years doing all sorts of residential building energy modeling work. One of the things that's really unique and powerful about this tool is that it's been such a cross-disciplinary approach and process. So we're considering grid impacts and not just building level. Michael, I'll let you go ahead and take it away.
Sounds good. So we'll start with a quick kind of background and motivation and then get into the specifics of the tool. So I think everyone's aware that we're in the midst of an energy transition. There's a lot of trends happening both on the supply side as we move from fossil fuels to renewables, but there's an equal amount, I think, of changes happening on the demand side, especially within residential buildings. So a lot of new technologies that are increasing energy efficiency, that are becoming more electrified, and many of these technologies are becoming more controllable and flexible as well. So heat pumps are electrifying our HVAC consumption, and smart thermostats are enabling more grid interactive and controllable use of our HVAC consumption. The same is true for water heaters, electrifying with just electric water heaters as well as heat pump water heaters, and this concept of smart water heaters that are more controllable. Same thing with electric vehicles, electrification, as well as kind of smart EV chargers that can control when to charge your car. Rooftop PV, as well as behind-the-meter batteries in residential and other buildings, are also increasing their adoption rates. So not only are we able to make our energy consumption more efficient, but we can generate more energy on site, as well as store that energy and use it when we need it. So many of these technologies are becoming smarter and more integrated, and there are other devices or tools for integrating all of these devices together. For example, home energy management systems, or even smart panels or smart meters that can control these different devices and coordinate them effectively together. Just to put some numbers behind these trends, these are some plots from a recent paper published by the Department of Energy, their virtual power plant liftoff report, which just gives some concept of the growth and the size of these trends. So I mentioned HVAC and smart thermostats, smart water heaters, electric vehicles and batteries. All of these are really seeing gigawatt scale growth currently in the near future. In particular, electric vehicle chargers, really staggering growth, I would say, in the up to 90 gigawatts expected of flexible capacity. And in terms of investment, this is already a very large investment in all of these different technologies, both in just installing them and making them, including them in residences, but also making them flexible and available for use to provide grid services and to provide benefits to homeowners and occupants. So, projections for over $100 billion of investment across all of these end uses by 2030. So as researchers focused on demand flexibility, we tend to try and ask questions like this. We want to understand what are the impacts of demand flexibility across a broad set of stakeholders. So maybe the obvious ones could be customers and grid operators, but there's really a wide range of stakeholders and a wide range of impacts that these stakeholders care about. And so when we're understanding changes to a new technology or new control strategies for these different technologies, it's important to think about all of the different types of impacts that these can have on different stakeholders. And so on the customer side, people often focus on affordability and lowering energy bills for customers. Occupant comfort is a big impact to consider there. On the grid side, grid operators want to provide low-cost, reliable service and make sure that the grid is resilient in the case of extreme events. And then there's societal impacts as well. So some of these technologies can improve or increase the rate of decarbonization of our energy systems, and they can also have impacts on equity. For example, changing, they can have impacts on customer bills, both for the DER adopters or participants who are engaging in demand flexibility, but they could also have impacts on non-adopters or non-participants. And so considering all of these impacts is really important when we're analyzing different methods for demand flexibility. We noticed as some of the existing tools before OCHRE was created that there's a bit of a gap between some of the more device-specific tools for evaluating demand flexibility technologies, more focused on buildings or vehicle side. And these tools tend to focus very specifically on the customer side, have very accurate modeling tools that consider the load diversity across different types of customers and the impacts, especially on energy bills and occupant comfort. And then on the other side, we have lots of tools that are more grid focused or focused on grid analysis that consider and really focus on the dynamic controls of these types of technologies, the impacts on system, on the grid, and the impacts on resilience and reliability of the broader system. And so there's a need to kind of evaluate the impacts of demand flexibility technologies holistically that considers both the customer side and the grid side and all of the impacts. And so that was really the impetus for creating the OCHRE tool, which we started 5 years ago or so, had been working on it ever since then. So I want to go into a little bit of detail on what the capabilities of the tool are and how it works. So OCHRE stands for the Object-Oriented Controllable High-Resolution Residential Energy Model, or OCHRE for short. The kind of primary thing it does, it has device level or end use level modules where it can simulate energy consumption for individual devices within a home, and it can control these devices and enable flexibility for each of these end uses. The main ones being heating, ventilation, and air conditioning, or HVAC, water heating, electric vehicles, solar photovoltaics, and batteries. For each of these, we can generate power consumption and load profiles. We can aggregate that up to the building level. And we also have comfort metrics, for example, the indoor air temperature or the hot water temperature, to make sure that the consumption of these uses are providing the grid service, or excuse me, the energy services that the customers expect from them. We can also model these in resilience scenarios, for example, if the grid goes down. And so these same kind of comfort metrics can be used to evaluate customer comfort during resilience or extreme events. We can model individual devices, just a single device. We can also aggregate that up to an entire home, and we can aggregate multiple homes to do community scale analysis. And a big focus of OCHRE and kind of one of its key features is that it can simulate or operate in co-simulation with many other tools, the main ones being device controllers or aggregators, DER aggregators, virtual power plant models, home energy management systems, as well as distribution system models that can communicate directly with OCHRE at a time-step by time-step basis. This is just a kind of overview of the simulation workflow. So the main inputs that Ochre receives are building and occupant characteristics, which we can get from a variety of tools. But these are things like the size of the building, the insulation levels, the types of equipment, the efficiency of those equipment, how many occupants and kind of what are they doing day to day. All of those characteristics, as well as weather data, those are the inputs to Ochre. And you can run Ochre by itself and simulate that home, or you can run it in co-simulation with these other tools like DER and flexible load controllers or grid system models. And that co-simulation can have kind of two-way communications where Ochre is sending information about the building to the other tools, and those tools are sending information about how to control the devices within the home. Once the simulation runs, we get outputs, kind of the main ones being load profiles at the end use level, as well as those occupant comfort and resilience metrics that I mentioned. So there's been a lot of focus on integrating Ochre with many other tools, many of them NREL developed, but making sure that we're bringing the best of both worlds from the buildings and vehicles tools, as well as from the grid tools. So ResDoc and BOpt are building tools that use residential building tools that use the Home Performance XML or HPXML file format, which Ochre can use and kind of import the building characteristics from those tools. We can also load weather data from NSRDB, the National Solar Radiation Database, as well as other weather inputs. And then we have device-specific data and tools like EVI Pro and SAM for the other device-specific models. And then we have integrations that Ochre can connect to in co-simulation. We're kind of the main co-simulation framework that we've used with Ochre is Helix, which has been developed by NREL and some other labs. It's also the topic of the next webinar next month. If you're interested in co-simulation, I really recommend that. We've also integrated it in with the GridApps-D co-simulation framework. It integrates with many different types of device controllers. Each project that we've worked on kind of has a different one, but the main one that's been used and one that's been developed by NREL is 4C, which is a home energy management system that can control devices in Ochre. It integrates with grid models. The primary one is OpenDSS, but any sort of distribution grid model or other grid model that can be incorporated in a co-simulation framework could get integrated that way. And it's also been integrated with planning tools like REOPT to enable demand flexibility analysis and dispatch in that tool. So I'll go in a little bit of detail on the different methods for control and communication in this co-simulation framework. Jeff is going to go into more detail on each of the end uses, but there's many different ways that these devices can be controlled. You can think about kind of a typical example is changing the thermostat set point for your HVAC system, and maybe the controller that's evaluating that thermostat set point is getting information about the indoor temperature of the building or the outdoor temperature. But we have many, many different control options across many different end uses. And Jeff will go into these in the later slides. The main thing that I want to mention here is the last row. We have some features that kind of control the entire home and its interaction with the grid. So we can run the home in islanded mode, simulating a grid outage. And we can also get information about the voltage of the grid, which we have voltage dependent load models that can change both the real and the reactive power of each device. So we have some interaction between the power consumption of the home and the voltage on the grid. With that, though, I'm going to pass it over to Jeff to talk a little bit more in detail on each of these end uses, as well as talk about the building envelope modeling.
Yeah, thank you, Michael. So I'll be talking more kind of specifics and some of the physics about how all these models work. So one of the unique, interesting things about OCHRE is it's a fully white box physics-based model when we're trying to determine energy consumption here. So for the building envelope, we can dynamically generate an RC envelope model to account for whether there's different unconditioned spaces, like an unconditioned attic, a crawl space or basement, an attached garage. And so we'll generate those unconditioned zones that will have their own model with their own temperature and humidity. And then all the R's and C's for all the different constructions, walls, ceilings, floors, etc., to account for all the heat transfer in the building envelope. We generally try to use simplified linear models for computational speed, but we can account for non-linear phenomena such as radiation. And then we also take weather data from NSRDB, or we sometimes use Energy Plus weather files as inputs. So the model will be sensitive to the ground temperature, the ambient air temperature and humidity, solar radiance, wind speed. And the model also accounts for if you have any equipment, like if you're cooking, that shows up as a heat gain in the space. Occupants being present also as heat gain. And we can also track humidity for primarily how that affects HVAC and water heater performance. Then going into some of the specific equipment models. There we go. For HVAC, so for any sort of heating and cooling, we can currently model most of the technologies that are available in BOPT or ResStock. So we can do air source heat pumps, mini split heat pumps, air conditioners, either room units or a central air conditioner, furnaces, boilers, and electric baseboards. In terms of heat pump modeling, we can do single speed, two speed, and variable speed and account for the differences in those technologies. Generally, as you get to more efficient heat pumps, you have more speeds. And so that sometimes opens up additional control possibilities in terms of controlling the speed of equipment. The approach that we're using here is based very heavily on what Energy Plus does for modeling the performance of these sorts of DX direct expansion coils. We're using performance curves that have been derived and used extensively for several years now in BOPT and ResStock. For air source heat pump modeling, we also do account for defrost. When you start getting to cold temperatures, you will have to see some sort of generally reverse cycle defrost to keep the coil operating. And so we're able to account for that. We can model ducts, although we do a somewhat simplified approach compared to what some of the Energy Plus based tools use. There is an approach specified in ASHRAE standard 152 for calculating the distribution system efficiency, which is basically the average efficiency of your duct system over the year. And so we use that to account for the efficiency of your duct system if you have a ducted system. The default control options here are doing thermostat with deadband, and then we can do kind of ideal control to maintain set point. The ideal control is kind of closer to how variable speed equipment operates, where it'll try to modulate to perfectly maintain the set point. We'll also use ideal control if you're trying to do simulations at pretty large time steps where you might actually have multiple cycles over the course of a time step. But if you run with shorter time steps, then we will actually account for having a thermostat with a deadband, and you'll get more real equipment cycles. When we go to the water heater modeling, we can cover most of the technologies that are available in the US. So electric resistance and gas storage tanks, tankless water heaters with whatever fuel you might use. And then heat pump water heaters is probably the most complicated option. We have a few different levels of fidelity for the tank model. So we can do it with 1 node, 2 nodes, or up to 12 nodes. By nodes here, I'm referring to kind of a 1D approach that accounts for stratification. So you would account for the fact that the top of the tank is generally warmer than the bottom of the tank due to buoyancy. These models have been validated against some detailed lab data that we've taken ourselves. So we've looked at what the power consumption and tank temperatures were for, say, a heat pump water heater under a typical day of hot water use. And then we've run that in OCHRE using basically the lab ambient conditions and draw profiles inputs, and made sure that we could get a good match on our model. The model here does account for all the heat transfer between nodes, the impact of water draws, and also the inversion mixing, basically the buoyancy effects where hot water rises to the top. In terms of control options, we can do, again, the ideal control and then more of the thermostat with deadband. We have also successfully been able to simulate some of the controls that are used on real water heaters. When we're comparing to lab data, we'll use basically the same control algorithm that the tank is using for validation purposes. For PV, we generally use PySAM and the PV watts model in there for modeling the PV. So we'll just load that directly as a Python-based tool. We can load other Python libraries. And so rather than trying to reinvent a new PV model, we are just leveraging all the great existing work that's already been done. This lets us model the PV, accounting for the capacity of it, the orientation on the roof, or if it's rack mounted, we can account for that as well. It doesn't have to be flush with the roof. And it's sensitive to weather data and all the things that you would expect to drive a PV model. We are generally just using standard default assumptions for the type of PV model and the inverter specifications. But we can model a smart inverter for reactive power. And so you can provide real and reactive set points, a maximum inverter power constraint, and then do watt priority or VAR priority modes. One other thing we can do is also provide a schedule file of PV data. So if you are either generating PV profiles from another tool, or you are trying to model a site and you have measured PV data, we could take that as a direct input rather than using the PV watts model. For the battery model, we did actually implement our own rather than just loading the SAM battery model. It is very, very similar to the SAM battery model, but we implemented our own model because this gives us a little bit of extra flexibility in the potential ways that we can control the model rather than just using what's in SAM directly. So the battery model is tracking battery power and state of charge. We do have a 1D thermal model for the battery, so we can account for any sort of degradation of the battery. In terms of control options, we can do daily schedules for charging and discharging. So for example, this might be arbitrage around a time of use rate, charge when your rate's low, discharge when it's high. We can also do target net load, so kind of self-consumption if you have solar and storage. Charge when your PV generation exceeds the house load, and then discharge in the evening as the PV starts dropping off. Or it can take a power set point from an external controller. So a HEM system like 4C could be sending power set points directly to the battery. We can also do islanded mode operation for resilience use cases using either a battery, or we do have a generator model as well. And looking at that powering any other equipment that we think is critical and ought to be powered during an outage. So that can potentially include powering HVAC, but we will model the thermal dynamics in the house. And so if HVAC isn't available, we'll know how hot or cold that house gets during the outage. So we can kind of predict what the impacts of that might be on either the occupants or the potential for property damage, such as pipes freezing during a long winter outage. For the electric vehicle model, this is using a lot of the battery model capability in physics, but we do need to know additional information about when the EV is present, when it leaves, and when it arrives, what state of charge it arrives at. So we are generating basically stochastic charging events for every simulation day. There's an event-based model for that generates the start time, the duration, and then the initial state of charge, what SOC the EV comes in at. We are using data from the EVI Pro tool for generating this. We will potentially look at updating this as more detailed data becomes available. Right now, we can account for level 1 and level 2 charging options, a few different vehicle types from plug-in hybrids to battery electric vehicles with different ranges to account for different battery capacities. There's also some variability to account for people using their vehicles differently on weekdays versus weekends, and the impact ambient temperature has on the battery in an EV. In terms of control strategies, we can do no control. So basically you get home and plug in immediately. We can look at delayed charging, and we can look at direct set point control. So we have a fair amount of flexibility in how you might want to control EV charging. We also have a sort of comfort related metric to unmet EV charge. So if you do apply delayed charging and you miss being fully charged, we'll have a way to track that as part of our simulations. For our other loads, pretty broad category here, but things like lighting, all your appliances, refrigerator, clothes washer, clothes dryer, etc. Any sort of miscellaneous loads, all the computers, gaming consoles, fans, all sorts of stuff, aquariums, whatever you have for appliances in your home. We're modeling those with a stochastic-based tool that's been developed using American time of use survey data. So American time of use survey data has people record what they're doing every 15 minutes over a long period of time. And so we kind of have an idea of what people actually do in their homes based on that survey data. And then we're able to take those responses, things like I'm showering during this time, I'm cooking during this time, and generate probability distributions for when people seem most likely to do different things. And then use that to generate stochastic events over the course of a year. So there's some examples here of the procedure for generating those and some schedules based on kind of clustering together similar occupants to come up with what are reasonable guesses at what people are doing at different times of days. So these schedules are actually coming to us directly from OSH PXML based tools like biopt and ResDoc. We are not doing the stochastic generation in OCHRE itself. But we're taking advantage of a lot of great work that other people have done to come up with this approach. All right. I do want to talk through some of the use cases here for OCHRE. So I'm going to talk through several, and then I'm going to let Michael talk through a couple before we open this up for questions. So the first one I want to talk about is a net zero smart community project. So this was looking at deploying HEMS and then also higher level aggregator controls in a potential new construction community that was going to be in Fort Collins, Colorado, consisting of about 500 pretty efficient homes that also had solar, and some homes had storage in them. So we were looking at deploying the HEMS on each individual home, but then also having higher level aggregator control and doing all the simulation with a grid model. So the aggregator can send signals to make sure that, say during peak solar times, we're not causing grid issues by maybe ramping up loads or things of that nature. And so this was kind of a precursor to some of the DOE connected communities projects that are currently ongoing. I'm going to talk about two of them that are using OCHRE directly. So one of them is called Salmon, Smart Grid Asset Load Management and Optimized Neighborhood. This is a project with Portland General Electric in Portland, Oregon, that's looking at building a pretty substantial flexible load resource in the study area. This is through a combination of connected devices, so controlling HVAC and water heaters, along with solar storage and EV. We've been using OCHRE as part of this project to actually simulate what would happen with higher participation as they're working on recruiting customers, and sort of what the controls might need to look like to avoid causing any grid issues, and sort of what's the benefit for the customer as well as for the utility to have this level of control. So we're trying to track the individual impact on the occupants, how this affects their utility bills, if they have any discomfort, say get a cold shower, because of the control, but then also like do this building to grid co-simulation and look at what the grid impacts would be of all these controls in coordination. Another DOE connected communities project that is using this tool is the AC3 Advanced Clean Communities Collaborative. So this is a project based in North Carolina that's looking at controlling HVAC and water heating in both new and existing communities. So we have some big builder partners who are building some new communities that are pretty efficient. They'll have heat pumps and heat pump water heaters, and then also some smart thermostats. And so we'll have some level of control as well as some water heater controls being deployed in these. So this project is looking at what the potential benefits of all that control is in coordination. We're using OCHRE to look at what it would look like if everyone's participating, the potential response to different control signals. One thing that's particularly of interest in this project is if you have air source heat pumps and they have electric resistance backup, if sending different thermostat signals might actually trigger that backup more frequently. And so you end up creating these unintentional peaks in the load. There's also a big focus on recruitment in this one and kind of looking at, how can builders kind of be part of the pipeline to getting people recruited into utility programs. So for some of these communities, we're looking at giving buyers the option to opt into a utility program as part of actually buying the home and signing all the paperwork. One other project is the smart panel evaluation. So we worked with SPAN in this case to kind of understand the potential benefits of circuit level control of a home energy management system. So for this project, we looked at in simulation and then in practice, what it would look like if we tried to deploy 4C NREL's home energy management system with a SPAN panel. For OCHRE, one of the things that we kind of focused on for this particular project was looking at what the potential benefits might be of knowing about a power outage. And so what the SPAN panel could do for you in the event of a power outage, if you know a power outage is coming, or if you don't know a power outage is coming, particularly for homes with battery storage. So there is somewhat of an increase in kind of known power outages. We had our first ones in Colorado earlier this year, where we had a high wind event and Xcel powered down quite a lot of homes in the Denver metro area. You're seeing this in California as well. But then there's also a lot of unplanned outages as well for a whole bunch of other reasons. So along with these OCHRE simulations, we evaluated the SPAN smart panel in NREL's SPL, System Performance Laboratory, and we did a field pilot of looking at deploying 4C on a real SPAN panel in someone's home. All right, Michael, I'm going to turn it over to you to talk about the last couple ones, and then I think we'll open it up for questions.
Great. So Jeff just covered a few use cases that were really focused on individual buildings or individual communities. We have a couple other use cases that are a little bit broader, focused on an entire grid system or a broader utility system. So the first one is looking at virtual power plant optimization. So this project was looking at wholesale electricity markets and how flexible resources broadly can participate in these markets. But one component of this project was how VPPs or DER aggregators could participate in these markets. And so we developed a VPP model that would aggregate flexible loads and bid those aggregated loads into the wholesale market. And then once it receives a signal from the market, it dispatches those loads in order to provide those grid services and minimize discomfort. So we used OCHRE and kind of connected OCHRE to this VPP model as well as the market model. We modeled 2,000 devices, smart thermostats and water heaters. So we created models for 2,000 homes, but we were only focused on controlling specific devices within those homes across a wide footprint. And so one of the things we found, we were using the comfort constraints as hard constraints. And it was the VPP or the aggregator's job to bid in the right amount of capacity. And if they bid in too much, then they wouldn't be able to achieve that capacity. So we ensured that the comfort constraints were met by the homeowners, but it was the aggregator was taking risk in bidding into these markets and determining an optimal amount of capacity to bid in order to maximize its revenue. Oops. Okay, and the last one is focused on the interactions between demand flexibility and retail rate design. So this project is currently ongoing, really looking at the dynamics and the interactions between customers choosing to shift their load based on dynamic retail rates, and how that impacts what those rates are through changes in utility system costs. So as retail rates change, that can encourage people to participate in VPPs and other programs. They can shift their loads, which shifts the load profiles. And if you're shifting load away from peak periods, that can impact the cost of service of the utility. And in turn, that again updates the rates for everyone. So we were looking at what different types of rates enable different amounts of load shifting, time of use rates, critical peak prices, that sort of thing, and looking at the trade-offs of these different rate designs in terms of affordability and equity, looking at the different energy bills for DER adopters and non-adopters, and then of course looking at customer comfort and kind of efficiency in terms of the cost of service to the utility. So these are all of our use cases. We've just got one slide on how to access OCHRE. I don't think we've mentioned OCHRE is open source. It's Python based. We have our code on GitHub at the link here. I think it was posted in the chat as well. We have some documentation and there's a good overview of kind of the things that we've talked about and some details on publications and past presentations at this NREL website link. But Jeff and I are the main owners and developers of this tool. We've got a few other people at NREL helping with us as well. But we're happy to talk with you all, answer your questions today. But if you've got ideas or are curious on how to use the tool, feel free to reach out and we'll be happy to help you with it. So I think we'll stop here. I see we already have a lot of questions in the chat, which is great. Just a reminder that you can click on the Q&A button in Zoom and enter your questions there, and we'll see them and we'll try and get through all of these. I think we got 20 minutes exactly, which is great. I hope we'll get through most of these. So I looked through a couple of them. Jeff, I'm going to give you the first one. For building characteristics, are you assuming those are known based on the home details, or do you have some parameter identification that can be done without details of the specific building?
Yeah, good question. So we are generally assuming that these are known characteristics because we are trying to keep this as a fully white box based model. Rather than trying to fit to measure data, which would be kind of more of a gray or black box based approach. So we are generally assuming that we know things about the constructions, the type of HVAC equipment, those sorts of things that can have a big impact on energy consumption. We do have cases where if we have limited information, we will sometimes try to make our best guess using probability distributions and kind of the likelihood that, if a building was built in a certain year, it might have less insulation or things like that. But we do need some way of estimating the physical characteristics of the building rather than just fitting to measured data.
Great. There's a question about harmonic loading, giving the amount of switch mode power and inductive loads that are present in residential buildings now. I didn't mention this, but the time scale or time resolution for OCHRE, we typically run at about 1 minute time resolution. We can also run at lower resolution. But some of the things that we don't focus on too much are kind of dynamics, electrical dynamics and harmonics. And so that's not something that's directly modeled in OCHRE, although you could, of course, take load profiles from OCHRE and based on when something is switching, incorporate other tools and use the load profiles from OCHRE to inform that. Jeff, here's two quick ones for you. Are there case studies on how OCHRE works with BOPT? And well, why don't you start with that one?
Sure. Probably the best thing to look for would be the CoRED project. That one was modeling a community in the Denver metro that was being electrified. And so we developed all those HUS models using BOPT. There is a journal publication and a pretty detailed technical report about that whole project and process. And so I think we have a link to the list of full publications. You can find any of the ones related to CoRED that there's that journal article and then the more detailed technical report. And that would probably be the best thing to look at. Yeah, I'd start there.
Can OCHRE handle natural ventilation? You want to cover that one?
Yes. Yes, it can handle natural ventilation. It can also handle any mechanical ventilation that you might have in the home. We basically use the same approach for doing infiltration and ventilation modeling that is done in our OSH XML tools. So we have more or less copied the infiltration model that they have. So we have the same level. We can have basically parity with those tools.
Great. I can take the next one. Could you explain how we access HPC resources to simulate, say, 1,000 models at a time, specifically with Kestrel and Eagle possibly no longer accessible? What are the alternatives? So really quickly, Eagle is, Kestrel and Eagle are supercomputers, high performance computing resources that NREL has. Eagle is being taken down soon, I believe, but Kestrel is not. So Kestrel will still be available. We have some, although limited, documentation on how you can run multiple OCHRE instances efficiently. We are going to be putting more information on that in our documentation fairly soon, but I do encourage you to look there, and there is some code that allows you to run multiple instances on a supercomputer if that's of interest to you. So that should be coming in the documentation soon. Also, just a quick plug that if you're a student, there's some, you can apply for time on NREL's HPC resources, and I don't have a link for that, but I know that some information about that just came out that might be of interest to some people. All right, Jeff, I'm going to throw this one at you. Which home automation applications does OCHRE interface with?
Yeah, okay, so OCHRE is kind of primarily more of a simulation tool. So generally our buildings are simulated, and so we haven't been deploying OCHRE on like real hardware and interfacing directly with, I don't know, Alexa or any other sort of automation platform. What we can do is if we know what the potential control options are of any sort of home automation, it can send set points to your thermostat, or it can turn off certain circuits or devices. We could always develop a simulation model of a home with that applied and kind of a baseline and look at what the impact is. But it's not something that we've currently interfaced with any like real hardware and real automation systems at this point.
Great. Okay, the next one is about time varying rates. We can simulate time of use, pricing, or fixed rates. How could we modify this to perform simulations based on real-time pricing where energy demand reacts to minute-by-minute price changes? So we can do this in OCHRE in a variety of ways. And there's some information about this in the documentation, but if you assume that you know what the prices are going to be beforehand, you can decide what you want to do and update that in the schedule before running OCHRE. So let's say you take a look at your real-time prices, your fake real-time prices, and you decide when you want to charge your battery and discharge your battery, or whatever the controls that you want to do. You can set that in the schedule and then just press run, and it will simulate the devices based on the schedule that you set. Another way, which is more realistic maybe for true real-time pricing, is to effectively have a controller in co-simulation with OCHRE that is receiving price information in real time and receiving information from OCHRE in real time within the simulation, and deciding what to do minute by minute. So at every minute of the simulation, the controller can send a new signal. It can say charge now, discharge now, change the set point. And so we can do that with any sort of dynamic price signal or other grid signal. If it's the grid goes down, or the weather changes, or whatever it is, you can change the controls minute by minute.
I might use this as a real quick opportunity to also plug 4C as being something that can use that sort of real-time price signal. And so 4C can do the multi-objective optimization between utility bills and comfort and potentially even emissions, if you want to consider that as part of the objective. And so we've done that in a lot of studies as well, where time of use or real-time price, whatever sort of price signal you have, will let 4C kind of decide what to do based on that price signal and maintaining a comfortable indoor environment.
Great. Next up, this is for you, Jeff. Have you looked at HVAC control governed by a temperature controller that takes temperature lift or outdoor-indoor temperature difference into account when establishing target temperature profiles? Results from comparing efficient heating cooling based upon set points could drive commercialization of residential temperature controllers and save large amounts of energy.
This is a cool one. So no, we have not. This is not an idea I've heard a lot about. I think you can write your own sort of custom controller. So we could write some sort of controller that is looking at outdoor temperature and adjusting set points based on that. This is not something we've really done yet. It's something we could potentially look at in the future, though. I guess I'll take this opportunity to mention that one other thing that we are actively working on right now in terms of HVAC controls is we have been working with a student who's been helping us to develop some more advanced controls for when the electric resistance backup on heat pump triggers, and try to make sure that we are realistically modeling when backup triggers compared to like how real thermostats would control the electric resistance backup. So we are doing some more active things on more detailed HVAC control, but this is not a direction we've really looked at yet.
Great. There's a question about integration with SAM. What are the key features you added which go beyond the SAM battery model? Are there plans to merge the two? So they're very similar, and the modeling is especially similar. I think there are a few differences in the controls. The only one, well, OCHRE is works in co-simulation, and I believe PySAM does as well. A small difference is OCHRE can run in self-consumption mode, but it can also target a specific net load output. So if you don't want to run purely in self-consumption, but you want to specify, charge if your net load exceeds 5 kilowatts or something, then that's something that you can do in OCHRE. But I think, yes, there are plans to merge the two. PySAM recently has enabled more co-simulation-like features and has some additional benefits in terms of the degradation modeling. And so I think it's on our list to better integrate those two models. There's a question on EV control strategy driven by smart controllers that seek to charge at the least cost times. Can the EV control strategy be driven by smart controllers that seek to charge at the least cost times reported by day ahead and real-time retail electricity providers? Yes. yeah, if you're given a signal, whether it's real time or not, it could be day ahead, it could be a time of use or anything like that. But the EV can be controlled in various ways. You can just do a simple delay. You can charge immediately and have no control. You can do a simple delay and say don't start charging until a certain time of day. Or you can have much more dynamic controls where you're setting the set point at any given time. And as long as you're staying within the constraints of the charging, the amperage constraints of the charger and the state of charge of the EV, we don't really limit charging that much more for EVs. How can we introduce inverter-based resources, such as injecting reactive power from a household with an EV or battery? This is a good question. So currently, we enable reactive power. We have power factor inputs for different devices, and we can set reactive power for solar. As of now, we do not have the ability to set reactive power from an EV charger or from a battery. That has been of interest, but it just hasn't been high enough priority for us to incorporate it in the model yet. But it would be fairly simple. We would do it in the same way that we did the PV model, where we would have reactive power, a set point and constraints on the reactive power or the power factor or the maximum, the inverter power limit. What are suggested applications for this tool? Jeff, I'll hand this to you. For example, might this be applicable to a utility program that aims to electrify homes of income qualifying customers while adding solar and battery storage?
Yes, so it definitely could be used in that kind of application. I do want to kind of suggest for applications that, there's tools like Redstock and BOCHRE that we integrate with. And depending on the question you have, then in some cases, you might just want to use Redstock and BOCHRE directly rather than using OCHRE. So those are Energy Plus based tools, and they do a great job at modeling all the building physics in more detail. So I would suggest, if you're looking at things like annual energy impacts and potentially even utility bill impacts, that you might want to stick with those tools. If you're interested in looking at controlling loads or building and grid interactions, then there's some really big benefit to using OCHRE for those. I would say that line's a little blurry, and so you can reach out to us if you have an application where you're like, I don't know which one to use. I get that question quite a bit, and so I usually try to point people to the best tool for their application. But as general guidance, I would say more controls and co-simulation applications are the best use cases for OCHRE.
Great. There's I think I'm going to skip the next question because the answer is similar to what you just said. Can this tool help with the total cost of ownership for batteries or EVs? How can the value of energy storage be accurately quantified for different stakeholders? This is a great question. I think it's maybe not a question that is directly answerable by OCHRE. There are a bunch of other tools at NREL that focus more on planning and kind of questions around the payback periods and net present value of different technologies. I would say OCHRE is more of an operational tool that's looking at how we control things in real time. And so for batteries, I would definitely point to the REOPT tool for understanding total cost of ownership. For EVs, I don't have a great answer, but I believe the EVIX tool suite has good information there. It's more focused on EV chargers as opposed to EVs, but I'm sure there are other tools out there that can give some information in terms of the cost of ownership for an EV and pros and cons of different tools there. I'll just mention also that OCHRE tends to stay away from anything related to cost. It's very much an engineering modeling tool. So we don't include things like retail rates or cost of adopting a DER technology. So those would be things that you could do as a post-processing step to calculate a customer bill, for example. There's a question, where did the physics engine for OCHRE come from, writing an RC network from scratch or from an already existing program?
Yep. So we ended up largely writing our own thing, pretty much from scratch. It follows, some of this is based on approaches that are out there in the literature, but we ended up largely just coding our own approach from scratch and kind of building up the complexity as we went along.
Great. This is a good one. You mentioned this is for homes. Can OCHRE also be configured to buildings, as a building represents a single structure with many floors, individual central heat pumps, or only individual homes or groups of them?
Yeah, so we have largely limited this to the residential space, either single family or multifamily. And so a big part of that is that we largely model the living space as a single zone with a more or less uniform temperature. I think when you start getting to more complex buildings, you want to actually account for differences in like temperatures on different sides of the buildings or across different floors. We've looked at kind of expanding into the multi-zone space, but I don't think we currently have any funding or plans to do that in the short term. And so we have largely limited OCHRE to residential applications. And I think given both the complexity of the more detailed multi-zones and all the different types of equipment, be that HVAC or things like refrigerator cases or other equipment, depending on the type of building, we're kind of not planning to expand into more of the commercial building space. I'm going to go back really quick, Michael. I think I want to talk to the ground coupling question too really quick. So Ron had asked about how we do ground coupling with like slabs or basements. Right now, we're doing the approach that used to be done in tools like BOCHRE that was residential, to kind of use a 1D approach to estimate the more complex 3D heat transfer. I know tools like BOCHRE and ResDoc are now using Kiva, which is a more advanced model, but we're kind of using the slightly older approach that those same tools used. So we do have an approach. It's been kind of developed and validated. There's papers about how it works. But it's, again, not quite as sophisticated as the Energy Plus tools.
Great. We had more questions, but I realize we're at time. Unfortunately, we're not going to get to them all, but I'm going to hand it back to Emily to close us out.
Yes, thank you. And if it'll just advance to the last slide there. Thanks so much, Michael and Jeff, for your presentation and for answering so many questions live. Our next webinar in this series will be presented by NREL's Brian Palmentier and will feature Helix, which is the hierarchical engine for large-scale infrastructure co-simulation. And that webinar will take place on Tuesday, December 10th at 10 a.m. Mountain Time, 12 p.m. Eastern. And you can register through the Powered By webpage, which I'm dropping in the chat for everyone right now. And with that, we'll close out. So thank you, everyone, for joining. Bye-bye.
Thank you.